Hello everyone, I'm Saeed Amiri from SUNY Binghamton, and today I'm presenting our work about reasoning with scene graphs for robot planning under partial observability. There has been an increase in the number of service robots in our daily life, and such robots are often used for object-centric tasks such as target search. But a challenge for such robots is that they cannot involve all surrounding objects in their planning model in order to make decisions, mainly because real-world environments are often filled with many objects. The goal of this work is to leverage graph-based contextual information for robot sequential decision-making. The proposed approach can be applied to other object-centric robot planning domains. We chose to demonstrate and evaluate it in target search. To address this challenge, we leverage the fact that objects are usually co-located with some certain objects. For instance, fruits are usually seen near other fruits in the kitchen. And we can form graphs to find out what objects are co-located with each other. Now the question is how to construct such graphs. To do this, we are using scene graphs that take an image as an input and output the detected object, their pairwise relation, and the bounding boxes. Using scene graphs, robot can construct a graph of objects that are near each other. For instance, in this figure, the scene graph shows a woman, a motorcycle, and their relation, which is the woman riding the motorcycle. But the robot's field of view would be limited and cannot capture the whole environment. To address this problem, we define two terms, local scene graphs and global scene graphs, where local scene graph is generated using a single image. And global scene graph, which is our contribution, is generated as the robot navigates and takes photos at different locations. We designed a framework called SARP. SARP stands for Scene Analysis for Robot Planning. We use partially observable Markov decision processes or POMDPs for the target search problem, where the state space consists of the target and robot locations. The generated policy maps the current belief to an action and receives an observation. Together, the action and the observation update the belief using Bayes update rule. In addition, we use scene graph datasets such as visual genome to train a network, where in this work we use pre-trained neural motif. Robot's image is fed to the network to generate local scene graph, and as it navigates, it takes additional images to augment and generate global scene graph. Next, it calculates the potential function for each edge of the graph to generate the Markov network. We calculate potential function by querying the dataset about co-occurrency of those objects in the dataset images. Finally, by doing reasoning about the target object, we bias robot's belief. We evaluated our approach in AI to Thor that consists of photorealistic images of household environments, where our approach, as shown in the blue box, was outperforming baselines by taking less action costs and more success rate in finding the target object. We also used a real robot with 360 vision for data collection and evaluation. Here is a portion of our demo where the robot is generating the local scene graph in order to augment the global scene graph and update the belief as it is navigating in the environment until the task is complete. Our robot uses scene graph to obtain domain knowledge and provide contextual information to the robot planner where limited perception is a bottleneck. The demo link and more details can be found in our paper. Thank you so much for watching this presentation.